Now let's turn our attention to example number 2. Suppose that we have F given as defined here, and we want to find the flux of F across sigma, where sigma is part of the paraboloid 4 minus x squared minus y squared that lies above this particular square. So you can kind of see in the picture that I have here that this is like part of a paraboloid. That's that parabola sort of shaped picture, you know, that would look something kind of like this had it been all the way kind of filled in. But we're only dealing with just the portion that's going to exist above this square that I have down here in the xy plane. Now, if I have this and I want to find this flux, again, I need to understand how I'm going to orient this surface, because this surface has two sides. And so which side am I going to consider as like top, or the positive side? Well, here we're told that we want to have upward orientation. So we want to have normal vectors that are going to be coming and have kind of like an upward tilt. Notice that if I was to grab vectors and go from the other side, I would have like a downward tilt that is represented by a negative z coordinate. So I want to make sure that we only have vectors with a positive or upward orientation. Okay, so we're going to try to have to go ahead and consider this as we go ahead and work through the question. All right, now what we saw in the last example was that it was important to start by creating a parameterization of our surface. Okay, so no big deal. So we first parameterize sigma. Okay, I'm going to go ahead and try to figure out a way to do that. So let's see. There seems to be a relationship between x, y, and z kind of all at once. Ooh, but this actually is really easy. Oh yeah, because this is kind of like a function, right? So if I just selected my x to be u and my y to be v, then it would be unbelievably simple to calculate the z coordinate, right? I would just do 4 minus u squared minus v squared, and I'd be done. And of course, the bounds on my u and v here aren't going to be difficult either, because if u is playing the role of x, and x goes from 0 to 1, u goes from 0 to 1. And in fact, so does v. So boom, we created a parameterization there in just a couple of seconds. All right, so if I want to go ahead and compute my flux, remember that I'm going to need to go ahead and compute my, oops, sorry, not the magnitude. I just need to go ahead and compute my r cross, or r partial with respect to u, crossed with r partialed with respect to v. So let's see. If I was to do this with respect to u, I would get 1, 0, negative 2u. And if I went with respect to v, I'd have 0, 1, negative 2v. Input here my I, j, and k. And then when I calculate this out, let's see what we come up with. So my first piece here looks like it's going to be 2u. My next piece looks like it's going to be negative 2v, or just 2v. And my last piece here is just going to be 1. Now, while this does represent a normal vector to my surface, I want to make sure that this vector that I have here actually represents one of these vectors. That is, one that would point out from the surface in this direction. And again, we said that since these have an upward tilt, we know that these have to have a positive z. So we know that that's got to be the case. We need to have a positive z in these vectors. And when I look at the vector that I created, it does have a positive z. So I know that what I've created here is the vector that points upward, tilts out in this direction. Remember, the other orientation that I could have gotten would have been a vector that would have pointed out in the other direction. And that would have had a negative z. And I could have gotten that by multiplying this by negative 1. That would have been negative 2u, negative 2v, negative 1. But since that's not the direction that I wanted to consider as positive, I wanted upward orientation, this vector I've calculated here needs no adjustments, which is really, really nice. Okay, so now that I have that, I'm ready to go ahead and set this up. So I can go ahead here and see that if I do sigma, I'm supposed to do f dot n dot ds, well, I should be able to change that out for my f, which again here is Oh gosh, that's really messy. That's x, y, z, zx. Oof. Well, before I go ahead and write this, how about I just write it in simpler notation first and then fill in the complicated stuff. So here, I know that I'm just changing it out for this. And then I want to go ahead and if I was to make this full swap, let's see, the vector f is a little bit complicated. Notice again that it's x times y. So if I go here, my x and y are u and v. So I'm going to have to change this to uv. Then I have to have y times z. Okay, so that's going to be v times 4 minus u squared minus v squared. And then my last component is going to be z times x. So that's u times 4 minus u squared minus v squared. So that's just f. Then I have to dot with this cross product. And then remember, I can select dA as in terms of u's and v's. So how about I just do du dv, and this becomes an integral from 0 to 1, 0 to 1. Now, I'm going to have to do this dot product first so I can simplify this down fully and actually then do the integrals. So let's see what the dot product would actually look like. I'm going to get 2u times uv. So this is going to be 2u squared v plus, I'm going to get all of this times 2v. So this is going to be 2v squared, 4 minus u squared minus v squared. And then I'm going to get plus 1 times my u4 minus u squared minus v squared. So this is actually a really simple integral to work with because at least it's just one big polynomial. Now I'm going to leave it to you to try to go ahead and work through the details, but I will tell you that if you do try to work through this all the way, we should find that the total flux is going to end up as 713 over 180. That's the total value that I got. I'd ask you to try to go ahead and before you move on to the next video, try to see if you can confirm that result by calculating this integral.